Okay, good morning, everyone. I'm Jeff Tsao. Kathy Simonson and I are the co-curators of Sandia's New Research Ideas Forum, our labs-wide vehicle for exploring and discussing new research ideas of labs-wide interest. We're pleased to host today a conversation on the topic of discovery research, what it is and how it can be better and more intentionally nurtured by human society and its institutions. Because of the widespread interest in this topic, we've opened today's session up to a public audience. So welcome to both the Sandians and non-Sandians who have joined us. Our speaker is Venky Narayanamurti of Harvard University. Many, and I count myself among them, think of Venky as a force of nature. He is legendary for the roles he played at Bell Labs in the 1970s and 80s, where, among other things, he nurtured many distinguished careers at the interface between material science, electrical engineering, and condensed matter physics. At Sandia as our own VP of Research in the 1980s and 1990s. At UC Santa Barbara as Dean of the College of Engineering in the 1990s. And most recently at Harvard as founding Dean of its School of Engineering and Applied Sciences in the 2000s. For those of us who have been fortunate to have had front row seats to one or more pieces of his career, he is also legendary for his ability to nurture, really nurture, his organizations and staff as human beings and not just as executors of projects and milestones. Before we start, a short note on logistics. The session will be somewhat informal and conversational. But it will have also some formality. Venky is armed with an extended set of slides to help guide the conversation. We may or may not get through all the slides, we'll see. Our conversation will go on for an hour, 9:30 to 10:30 Mountain Time. Then we'll open Q&A up for those interested in staying for an additional half hour from 10:30 to 11 Mountain Time. Because of the size of the audience, we've automatically muted everyone, but please use the chat window throughout the hour and a half, and we'll try to keep track of comments and discuss as we can during the last half hour. We will be recording the full hour and a half, and the recording will be available both to Sandians at our Sandy internal NRIF website and to non-Sandians at the author's website you see at the bottom of this slide, discoveryresearch.org. With that, let me turn the microphone over to Venky to say a few words, and then we'll start the conversation about the ideas in the book.
Well, thank you very much, Jeff, for this very kind introduction and for hosting on behalf of Sandia this talk. In many ways, I think it's very appropriate that we are doing this first book talk together at Sandia National Labs. I, as you mentioned, was at Sandia for almost 5 years and then also continued on many advisory committees at DOE, including in inertial fusion and other areas. And I want to acknowledge, especially for the Sandians, the enormous impact my own coming to Sandia had on me. I had worked for Bell Labs for so many years and with the communications and working in that kind of research. But Sandia was a much broader organization. It had a national security mission. It had a mission in energy and environment. And then over a period of time, a significant mission also in technology translation, where through cooperative research and development agreements. So it was an enormously broadening environment for me, and I'm very grateful for that. The other is its public service mission. I've always felt education is also part of public service, and Bell Labs and AT&T was also always about national service. So the public service mission, and finally the attitude of Sandians, a kind of can-do attitude, problem-solving attitude in the highest standards of engineering excellence. Those were important things which I learned specifically. Secondly, I also learned a very important feature of redundancy, of all of those features which are important so that in fact you minimize errors and false alarms. So there are many, many other features which I can't say or enumerate, but these are just some which occur to me spontaneously. So I have a great deal of affection for Sandia because of its national service mission. To that, I want to now acknowledge my co-author, Jeffrey Tsao. He was a young MTS at Sandia when I was vice president, but I heard a lot of good things about him from the center directors at 1100, Fred Wook, his department managers like Paul Piercy and Tom Picrow. And as I left, he was actually appointed department manager of a new organization with Paul Piercy. And so I think, and one other point, Jeff was also actually a PhD of Harvard of the division of, at that time known as Division of Engineering and Applied Physics. And so in a sense, I guess I, as the former dean, can have a certain claim to Jeff in multiple ways. It's been a pleasure interacting with him. He started with a lot of questions. When he came first to Harvard about 4 years ago in 2016, and we had enormously long conversations. At the end of each day, I used to be exhausted, and in the morning he would produce these beautiful notes of everything we had discussed. And these questions and answers morphed into a debate between the two of us. And we thought we'll just write a short paper, but it ended up ultimately in this book. So Jeff, thank you for your very wonderful collaboration this past 4 years.
Thank you, Venky. I have learned so much more from you than you've learned from me, though. But, okay.
Yes. So I want to acknowledge before we start the conversation the also several people. Some of them are Sandians. Some of them were my colleagues or are my colleagues at Harvard and other institutions, and some who really came because we were writing this book. And they span many disciplines, from computer science to biology to social studies of science, etc., and also public policy. And they're listed here, and they all gave many of them went through the manuscript, early drafts, and made enormous number of very useful comments. After we finally submitted a manuscript to Harvard University Press, I said, this is the submission. Harvard University Press had a couple of outside anonymous reviewers who actually were amazing. In fact, the one anonymous reviewer made so many comments that, in fact, Jeff and I had to do several rethinking to be sure and that we were addressing the issues. And then we've got further comments from the faculty editorial board before it was finally approved for publication. Then they asked me and Jeff to name some people who might be further reviewers, but they'll be public reviewers and might comment on the book. I gave them about 12 names, and the 4 who actually seem to have, they have asked, they usually want 3 to 5. That's the number which they want. And so I'm very grateful to Laura Anadon twice, Nancy Andrews, former dean of the Duke School of Medicine, John Holden, now my colleague, but President Science Advisor for President Obama for all of 8 years, and Keegan Zhui, one of China's most distinguished physicists, winner of their science prize, and he was for a long period the president of the Beijing Academy of Quantum Information Science, which is a huge and future undertaking. Our own lived experiences, and of course, my own environment at Harvard, Kennedy School, and of course, in Santa Barbara and many other institutions, and without question, in the current environment, Sandia National Laboratories. We have also benefited greatly. Of course, our book, which is, at least we have copies, I don't know whether they're available in bookstores, so it's a real thing, it's not something imaginary, is 80,000, 90,000 words and large number of references. Believe me, Jeff would not give me a free moment unless the references were all included. So there you are, but I still made him choose some special ones which we think were critical, and they are listed among the whose work we were especially influenced by, but obviously there were many more. So that's sort of how I think it summarizes what we were talking about in the book.
Mm-hmm. Yeah, and let me interject that there are a lot of books on research policy, research management, and at the beginning of the project, I guess we also, weren't quite sure how the project, as Venky mentioned, was going to turn out. I think we surprised ourselves, with this debate that we had and the questioning and answering that we went through many times during these few years. We were surprised at some of the new insights that we came up with. So we're quite happy with how the book turned out. It is not just a regurgitation of a lot of other, I don't know, maybe one might call them platitudes about research. Okay, so maybe let's start off the conversation with maybe the first most basic question, Venky. Why? did we or you write this book? What was your motivation?
So this particular view graph is just a very high level summary, which is there in terms of the book, because we actually believed that that the nature of research needed a significant rethink as deeply holistic and its nurturing as deeply human. So what do I mean by that, and how did we actually come to that conclusion? After I stepped down as dean, I was invited to be, John Holden was going to President Obama as science advisor. Graham Allison, then director of the Welfare Center, asked me if I would. In fact, the whole area of science and technology policy was started by a predecessor of mine at Harvard as dean, Harvey Brooks, who actually was a sort of the dean during Jeff's time and when he was a student. And anyway, I then started teaching courses on science and technology policy to the master's students at the Kennedy School. They're the ones who go to Washington and make these things. And you start with Vannevar Bush. The reason Sandia was created was right after World War II. It was the X division of Los Alamos. And I read his papers. They were legendary. They read his book, his report to President Roosevelt on Science, the Endless Frontier. It was really quite an amazing piece of work. And then I started analyzing this report. And I had a postdoc, Tolu Odomusu, who was my assistant. So I told him, read Bush's paper carefully and tell me how many times he refers to science. Because he said science, the endless frontier, and how many times does he refer to engineering? So he said, well, it was science maybe 100 times and engineering 4 times. I said, what are the examples he chose for this? Of course, nuclear weapons, which caused the end of World War II after President Truman's decision. Then there was proximity fuse. There was synthetic rubber and radar. And of course, all of them, I associate proximity fuse a lot with electrical engineering. I associate synthetic rubber a lot with polymer and chemical engineering. I said, we're somehow not quite conveying the quite thing how science and technology work. And then at Bell Labs, I'd already learned that you never separate basic and applied research. You really, research is something which is unique. So I felt this needed serious revision, and I wrote a book with Tolu Odomusu, Cycles of Invention and Discovery. And that was that. But when Jeff came on, he asked so many questions, and we realized it was only part of the story, that there are many other ways research functions, and that some which scientists have solved, some engineers work with, and some with policymakers and business school work with. And so I actually, the one difference which Jeff and I had for a long period, Jeff is very much towards reducing things to its smallest denominator, reductionist thinking. You know, I'm a nanoscientist who started in very, very esoteric low temperature physics. But I really thought engineering's biggest role was its integrative function and the holistic nature. And this is so important, and it has to be managed or run in a different way than anything else. At the same time, you want to think about doing new things. So it needed both a new exposition of the holistic nature of research and the nurturing, which is so important for creative people. So I hope I've expressed that, Jeff, fairly.
Right. I guess I could maybe add that.
So I think one of the important goals of the book is not to just ask for more money, but really that the reason we want to do this is to make what we do, including research, more effective. By more effective means that really the key role of research as looking for surprise, looking for novelty, looking for creativity, looking for all of that, because that is the more done in the right way, which means you also need leadership where somebody who knows how to fertilize the flowers and kill the weeds. If there's nobody to kill the weeds, then they will overtake the flowers. So you need the combination in proper way, and this is really important. And still, people look at me rose-eyed, what does this man mean? But this is, I think, really quite important. And we'll come back to this as we move on. Right. But nevertheless, there's another reason. There are many alarm signals. The big industrial laboratories of the past, Bell Labs is of the past. It got broken up, and so is true for many others. And really, that is not how other countries are doing it. And many national studies by very well-known people rising up of the gathering storm, which is when I started teaching public policy in about 2008. And then in 2020, I was part of a panel which was chaired by Neil Lane and Norm Augustine. Norm Augustine, former chairman of Lockheed Martin, which was the next sort of manager of Sandia after AT&T. And they recently produced a report, The Perils of Complacency, which has had a big impact. And so if you go to the next slide, Jeff, we in that, and Jeff reanalyzed some of this data here, that there is clean competition, that science and technology has become the main battleground. Now, we don't view it that way. We actually view research as global, and it's very important that we be in that global place. After the two of us, Jeff was born here, but obviously his parents came from China, and I was born in India, but came at a very young age, but we are now very much American. So it is research, and for talent is global, and so is Sandia global. And it is kind of interesting to see what has happened to the US compared not only to China, the other important feature, even with regard to rest of the world. We are now actually falling behind not only China, but also the rest of the world. And it's not, I believe, just about the money. It's because how we do the research that we lost that culture of Bell Labs just being the iconic name, but a lot of famous industrial laboratories in different fields of study. And that they never separated basic and applied research or science from engineering. So I hope that is clear as to why we wrote that book. So if we go to the next slide, it turns out that finally policymakers are realizing that even though we want to celebrate Vannevar Bush, another alum of Harvard, by the way, and former dean of engineering of MIT, and was obviously a great man at that time, that really we need to rethink national science and technology policy. And there have been two bills in Congress, one from the House and one from the Senate, where there's a great deal of debate as to how this should be organized. But everybody agrees that there needs to be a revision of the rubric under which science and technology operate at the national level. So I think that's sort of my view. And I know Jeff always has questions of me. So Jeff, have I completed what I think needed to be said?
Yeah. Let me just amplify on the, it's really easy for researchers to sort of become a special interest group and to say, oh, we just need more money. But yeah, I think the whole idea here is it's not just more money. Can we make the money that we already have more effective, or whatever money we have more effective? And yeah, that's the.
Yeah. And so many of these studies actually have been highlighting the need to break these boundaries. One of the books, as we have the readings, I chaired a committee of the American Academy of Arts and Sciences in 2013, where I actually articulated this along with other colleagues, this need to actually look at this interface and really go into a new domain of how science and policy. So this next view graph summarizes in one page the core reflections of the book. For me, when in this debate, I still remember in Pierce Hall, which is a very old Harvard building, where Jeff would meet in my office, and we kept on debating because we knew science and technology are not static. They keep changing, and we knew that all the time. And then as we were drawing diagrams on the blackboard, Jeff, with his mathematical instincts, put a dot on S and a dot on T, and certainly it said that's the right attitude, how to draw the diagram. Science and technology are not static. They are dynamic quantities. They evolve, and they do an enormous amount of interplay between each other. And Jeff will go into this in a little bit more detail here. And it is so important that it is not S and T which we are talking about. They're important, of course. They are the repositories, but it's really the dynamic evolution of science and technology and how they work together. Second, there are many other ways, of course, you can think of research and development and all these other features. And some of the great people in this field was, of course, Popper, who talked about hypothesis testing, and Heilmeyer, who was one of the legendary leaders of DARPA, which is a legendary organization, especially in the defense area. And we will come back to that, that finding questions is just as important as finding answers. Constructivism is just as important as reductionism. I don't want any engineer to think they are inferior to science or science is inferior to engineering. It is the holistic combination of the two. Questions are networked and answers are networked into a seamless web of knowledge. The next point, Thomas Kuhn wrote a famous book, but it's about scientific revolutions. He completely forgot, and other people have recognized that technology, in fact, was before that. And nevertheless, we actually have to think about knowledge more with regard to what happens in biological evolution. And in fact, engineering and biology have a lot in common. One of the important ways I was able to convince President Larry Summers, he was, a very demanding boss, but a wonderful boss, as to why Harvard should have a school of engineering. It was because I said life sciences are going to be intimately related to engineering and computer science and applied mathematics, and that's going to be very important. In fact, the more I thought about this, and we've been thinking about it, there are enormous interfaces because there are integrative functions as different from reductionist physics. That doesn't mean reductionist physics is bad, but it is different and important to understand. So we use the language of biology, of punctuated equilibria, require both surprise and consolidation, and that really exploring the frontier of knowledge means both. And that seeking surprise cannot be scheduled or projectized. Consolidating the frontier of knowledge strengthens and extends what was surprising. And the meta goal of research is surprise. It is not the same of meta goal of development. The meta goal of development is to make things work and to make sure it works. It's extremely important and very consuming. This is not to minimize that importance, but they are different. So we have beyond Bell Labs guiding principles for nurturing research. And I want to again emphasize, I will use the word Bell Labs mainly because that's the one I know the best because I worked there and I've studied it. But there are enormous number of other industrial labs from IBM to GE to RCA Labs, DuPont, Xerox PARC, who have actually in many ways symbolized the same thing. It is a different kind where they don't ask, is it science or is it engineering? Let's go solve this important problem, bring all the best ideas to bear. So now, if you look at the history of biology and other areas, it is clear that we need to rethink. And that's been happening over the last many years, including new constructs in universities, at Santa Barbara, at Harvard, at MIT, and everywhere else, and also in other places. So we will talk more about this as we move on to the rest of the talk. So I think the book has 4 main chapters with bound by an introduction, which actually gives you a feeling for this, what I've just been through, and a conclusion of what we see as the future. But the main chapters actually try to explore in detail these different concepts, the relationship between science and technology, questions and answers, punctuated equilibria, and then the nurturing of research. So the first, it is the relationship between science and technology. And of course, I've already mentioned that we actually I believed after finally teaching and after glorifying, and Bush needs to be glorified because he was actually a wonderful leader, but he was thinking at a certain time in a certain place. 20 years later or 40 years later, Donald Stokes, even though others had recognized this, but it never made it into the public. And until Donald Stokes wrote this book, which became common reading for a lot of policy students, etc. But technology can also be a pacemaker of scientific process. And of course, it is a deep flaw because so many times the technology came first and then the others. If you know, you can look up, you can start arguing, is why more important than how, or how important than what? And it's clear all 3 are related and you don't elevate one over the other. In fact, what Tolu and I decided to write, I said, we needed to change the language and wrote a book which really delved on this point and really went through a lot of examples, especially Bell Labs examples, in cycles of invention and discovery. So many people, including Jeff and others, including some of my collaborators who reviewed our early manuscripts, why did we actually, what is there new? The new is really understanding the rest of the web of the knowledge, the questions and answers, the constructivism, and how it relates to the great theoreticians who had actually studied these subjects. and then actually spell out in greater detail the key characteristics of leadership, which are so important, and governance and organization, which are important. There are many things which were done correctly 70 years ago, and sometimes you have to relive the past because it was done correctly, including how national laboratories function, how industry functions, how universities function. So so it needs to bring a more holistic thinking, where it's not just the Bell Labs point of view, but integrating all of these different point of views. And the reason we chose the title Genesis is because, in fact, that is what is the source of the revolutions, including the ones in physics, my field of physics. Sometimes, of course, science is more dominant, sometimes the technology is more dominant, but more often it is the integration of the two. So I think that's really what I now want to have Jeff discuss a little bit more about this key part of chapter 1 about the technoscientific method and T dot and S dot.
Okay, so I'll chime in a little bit here. So this is something that we call the technoscientific method. There is a lot to this graphic on the left, and actually we could easily spend an hour on it. So I'll try to just summarize as quickly as I can. What Venky and I have done is made explicit what science and technology are and how they evolve and interact. And as Venky mentioned, in fact, it's easy to confuse what they are and how they evolve, just like it is easy to confuse people who know a lot of science with people who create new science. So in our view, science and technology, which we denote by these symbols S and T, are repositories of knowledge. So science as you see on the left here, science as facts and explanations for those facts, and technology as human desired knowledge, as human desired functions and forms that fulfill those functions. The way science and technology evolve and interact, what we denote by the symbols S dot and T dot, Venky's already introduced those, are the scientific engineering methods. That's processes 1 through 6 on the graphic, function finding, form finding, and exapting for the engineering method, and the beautifully symmetric fact finding, explanation finding, and generalizing for the scientific method. And for those of you who haven't heard of the term exapting, that's a term borrowed from evolutionary biology, which basically means the co-opting of forms for new functions. I think the most important point is that even though S and T are separate entities and they can stand alone without the other, they are mixed when you consider S dot and T dot, when you consider how they evolve. In fact, they cannot evolve, or they at least cannot evolve very effectively without each other. So, again, there's a lot to this figure. It'd be nice to spend, maybe we'll spend another hour, Venky, at some future date on describing this figure.
Yeah. So even in this chapter, even though some parts of it are there in cycles of invention and discovery, there's a much deeper articulation here of actually what this is all about. So I think that's actually true that we have built on that work. The second chapter is really about the intricate dance of questions and answers. And again, I already had mentioned that, Hallmeyer is very well known in DARPA circles. He laid out a whole bunch of benchmarks of what a person should be do or would do. It was really to find answers to some particular question. Why do you think your approach will work? Who cares if you're successful? What are the risks and the payoffs? How much will it cost? How long will it take? What are the midterm and final exams to check the success? So not that this is wrong, this is bad, this is good. Obviously, DARPA is a very successful organization. But in terms of the research end or the science end, it is still limited. Because part of the science end or the research or technology end is the question part. The great technologists always are questioning. Steve Jobs may have used the work at Xerox PARC and Bell Labs and IBM and other places, but he thought in entirely new way of putting these things together, including the human touch of actually having a touch-sensitive display. At earlier times, Einstein actually completely upended Newton's laws with the gravitational theory of radiation, and in a more limited way with the special theory of relativity. And he said the formulation of a problem is often more important than its solution, which may be merely a matter of mathematical or experimental skill to raise new questions, new possibilities, regard old questions from a new angle requires creative imagination and marks real progress to advance in science, he says, but I would say science and technology or science and engineering, because I see science very often as a conservative force. Even engineering can be a very conservative force. But I view engineers as the great inventors who changed the world. It is Edison, it is Graham Bell, it is Shockley, it is Bratton, and so on. And we can go that. And that has not to be forgotten. It's not just science. It is a combination of science and engineering. It's really important, I believe, and if nothing else, that is so important. That's why we think it's the techno-scientific revolutions. It brings the true union of both the experimental and the theoretical and working together, where sometimes you emphasize one with the questions, sometimes you emphasize the solutions part, and you need both. And so, in fact, techno-science advances in an intricate dance of question and answer finding. So, Jeff, maybe you want to say a little bit more about this intricate dance. Yeah, let me interject one other thing. That okay.
Well, yeah. No. Why don't you keep going, Venky, on this piece, and then I'll.
Okay, I want to recognize, because of course Jeff brought enormous number of literature because he'd been reading things from a different angle, and I, because of my condensed matter physics background and Bell Labs, was always surrounded with people who were curious, who want to do something new. They never asked, is it science or engineering? Is it physics or electronics? They said, hey, what's the most exciting problem to solve? And the theorists never sat in their ivory tower. They came into the lab and talked to you. And one of the greatest such people, one of the greatest so-called theorists of all time, was Phil Anderson. And he had many an argument with high energy physicists. And in fact, historians of science and technology have written books about the solid state insurrections. It's like those who did January 6th or whatever, that the solid state upstarts, that Phil Anderson were upending the basic parts of physics by calling that more important. Because Phil Anderson wrote a famous paper in Science, which only more recently got recognized with Santa Fe Complex Systems Institute, etc., that more is different. That whenever you go to complex systems, new things arise. And in fact, they cannot be started from simply the physics laws in a simple way. At least we haven't learned how to do it. Maybe somebody will learn how to do it. And in fact, entirely new things happen. And there is enormous creativity at all levels of this complex system. So this is really important. And you don't think of chemistry as applied physics. There are people who have said very nasty things about chemistry, physicists. I do not want to, and same thing about engineering, as if engineering is only applied science. Engineering, as Jeff already pointed out, is a lot about new forms, new imagination, design, all of those other features, but science is also important. And so these disciplines and these areas are really areas, especially for complex systems, where entirely new things arise, and they're not. That's why both reductionism and constructivism is important. So Jeff, maybe you want to now add a little bit about from the previous view graph.
Yeah. And actually, well, even just on this view graph, I think one of the things is about questions and answers is that they're nested, of course. There's a hierarchy. You can start with a question, you can answer that question, but that answer itself becomes a new question. And then when you answer that, then that new answer becomes yet another question. So there's sort of this nestedness that spans all the way from elementary particle physics all the way up to social sciences. And I think the point that Venky is trying to make is that one might think, and some physicists have thought this in the past, that, the further down you get in this question and answer chain, the more important it is. I think what Venky is saying is that that's not the case at all. At each level of this nested hierarchy, there are important new questions, important new answers.
It's very important that the arrow go both ways. Even that's not quite, it's really a web of knowledge. It's really important to recognize this. Those who think about complex systems are beginning to recognize that. Very recently, the Nobel Prize in Physics went to that. So it's really quite something that finally, they take a long time for contrary ideas to be understood. And that doesn't mean high energy physics is bad or elementary particle. It's a different function. It is a frontier of physics, but it is not the only frontier of physics or engineering or whatever.
Right. It's a much more egalitarian view of where the important knowledge is. Biology is not subservient to physics. And social science is not subservient to biology either.
Yes. Yeah. So the next one actually is what is a very good one, and I think Jeff should say a little bit, especially about technology. But both were fine. Go ahead.
Yeah. So let me comment on this one. So as Venky was talking about, in our view, question and answer finding is also a cycle, just like science and technology, or S dot and T dot represent a cycle. You might start with a question, either a scientific one, like on the upper left here, why is the speed of light constant? Or it could be a technological question, like how could we do spectroscopy better? You then expend a lot of effort trying to find answers to those questions. But those answers, the best answers anyway, are almost always reusable. They not only answer the original questions, but they also answer new questions. Special relativity, for example, didn't just explain the constancy of the speed of light. It unexpectedly also explained the release of energy during fission and fusion. The laser wasn't just a form that fulfilled the function of spectroscopy, but unexpectedly turned out to be a form that also fulfilled the function of communications. So finding questions, again, as Venky was saying, is just as important as finding answers, but and it requires just as much effort as finding answers. But the key thing, as we all know, in terms of sort of the current way in which research is funded or research is nurtured, no one can write a proposal to find questions. So we end up supporting and encouraging only half of the research process, the answer finding half. We don't support the question finding half. Now, the question finding half, that other half, may be done anyway, just because I think all researchers instinctively know that it must be done. But without support and encouragement and sort of active nurturing, it's done in a crippled kind of way.
So I think I want to just add one more thing about this. It's a nuance because we talked a lot about Bell. Towns was, of course, first started his research career from Columbia at Bell Labs, and then became only a consultant and started working at Columbia because in the early days, the Bell Labs management didn't think it would have big impact on communications. And it was, so nobody thought, in fact, laser, that optical communications will become so important. So even, of course, great institutions, Harvard has made mistakes. I'm sure DOE and Sandia has made mistakes. That's all right. But this is an important thing that sometimes you do not fund those important people. This includes in theory and questions, because in fact you can't prove it. As we say in our book, Darwin would probably not have been funded, or Einstein. And there's numerous cases of technologists. Herb Kromer, my colleague at Santa Barbara, who got the 2000 Nobel Prize in Physics, actually left Varian because they thought didn't have enough applications. So it's very important to allow a small subset of people, there's obviously a judgment call, to actually give that run for the greatness of institutions. Secondly, actually, if in fact you discover that you are actually, that the science part or some physics part is more important, start doing that. And I'll show you some examples of that, and not just say, no, we hired you to do this. That's what a great research organization does. Am I being clear? And no, very often the funding and Office of Management and Budget, DOE, it gets constrained because of the OMB, because the economist said it should be spent this way. And instead of recognizing the research is about surprise, you should be able to move from one to the other. The thing which I've been fighting for a lot in my post-decadal career, where I was no longer viewed as some administrator, about these flexible funds for DOE laboratories. It really is important. They're a national treasure, and they're the only hope to replace the industrial labs at scale, because you need scale for many things. It's not like software. So I'm sorry for interjecting, but I think this is important, actually, why we are writing this book, and hopefully people will listen, and hopefully that legislation will, and then we can argue what the name should be for research. I think it should be called not National Science Foundation, National Research Foundation, or maybe National Science and Engineering Foundation, because they have the right, because they're the scientific method and the engineering method, and union of those is the research method. Am I being clear, Jeff? Have I answered? Because that's a question I've been asked by you, by Laura Anadon and others, and this is the answer.
Yeah, in fact, what Venky and I are calling the union of the scientific and engineering methods, we're calling that the technoscientific method, right, to kind of make it clear that.
And this is not, science is very important, and engineer, and we don't separate these out in kind of That's what Bell Labs always said. You didn't separate basic and applied research. Somebody called it pure research, as if everything applied is impure. So it's really important that we change the language and really appreciate this holistic nature in its finest sense, which is where the world needs to be. So the next chapter 3 is really goes far beyond Kuhn, because in fact, Kuhn talked about paradigm creation. Of course, and Jeff did especially a lot of thinking about paradigms and how they relate. And we came to the conclusion that actually what the biologist did is a better way of describing what happens. Paradigms are important, but in fact, it's the punctuated equilibria of surprise and consolidation. And both are important. Consolidating, extending conventional wisdom are important. In some ways, Moore's law is part of that, and it's extreme. And some of the advances are due simply to the cumulative advances in computational power, which has led to a whole lot of new things. And of course, surprise and overtake are also important. And you know many examples are heavier than air, et cetera, et cetera. But one example which we study in detail is actually solid state lighting and its precursors. And Jeff has done a lot of work in that area. I myself have been involved with gallium nitride research at Santa Barbara, which is a preeminent place in that area. And believe me, nobody believed that highly defective semiconductors would emit blue light and change how every light bulb, all my bulbs in my house are LED bulbs because I feel a certain affection towards them. And even though I paid a little bit more for them, they don't burn out. I've not changed a light bulb ever since I got them. Before I used to keep changing the bulb. So I think it's very important. Nakamura will tell you when Jeff wrote a review on that in fact, nobody would attend his talks. And afterwards, there would be like a rock star because suddenly it was important. So, and Nichia didn't want to fund him for a while. He actually ended up at Santa Barbara. He's now a United States citizen and a real contributor to US science and technology. So again, technoscience advances in cycles of surprise and consolidation. And we need to really recognize that both are important, but we have to view them in a slightly different way, but not elevating one over the other. So we have done a lot of scattered examples throughout the book, but some we studied in great detail where we knew something about. One was, of course, as I already mentioned, about solid state lighting, actually lighting, which is the end of this chapter 3. But one of the things which I wanted to emphasize, which is part of even cycles, but not in this detail, is really the science and development, science and technology, and the research and development, how they are viewed. Because it's the dynamic changes which were occurring, and research and S dot and T dot can be in both phases. On the engineering side, it's also a paradigm creation and surprise, and revolutionary science can be the fractional quantum Hall effect. So the left-hand side, they were all in the same lab, Solid State Electronics Research Laboratory, which I was fortunate to be director of, but these were these great researchers. My only contribution was that when Horst Stormer invented modulation doping and then went along with Dan Suey and did the fractional quantum Hall effect, and I didn't know what he had observed. He came to my house with this data. I said, I don't know what this is. I told everybody at Bell Labs, but it's something important. He's seeing fractional numbers and the charge is supposed to be integral. I had no idea what this was all about, but then we decided this was important. And the Bell Labs management, including Arno Penzias, was a very demanding vice president of research, said, go, that's what we should be doing. We didn't say you were hired to do modulation doping and make high electron mobility transfers. At the same time, we had others working on high electron mobility transfers, which were also important because they were important for wireless communication. So this is very important that sometimes DARPA and others do not allow you to go into that phase. This is an extremely important thing. And so there are, and science has normal periods. So now hundreds of people have been studying fractional quantum Hall effect, and hundreds of people have been improving MBE. Not that that's important, but it's a different function, and how you actually organize it becomes important. So research and development encompass both S dot and T dot. So I think I always like to say this as a summary, that research and development, will you show the next view graph, Jeff? We understand as an unscheduled quest for surprise and unexpected, whose outcome cannot be predicted in advance, and almost always Science and engineering are essentially different. You can call it science and technology because, in fact, they're the tools, the engineering method, etc. And of course, sometimes, but you don't force this. You let this happen naturally. That sometimes, depending on what happens, you might actually start emphasizing the science some more, that is, understanding the physics more, or sometimes you might start understanding the development of the technology more, or whatever. So both has to be, there needs to be wise management or leadership who understand. They don't manage it, they'll allow you to do that. You don't put people in narrow stovepipes. Development as a scheduled activity, because there ultimately, especially if you're doing a product development or others, an extension knowledge with a well-defined outcome in a specific time frame. Because if it doesn't come out, then you abandon that project. That's fine. And that's okay. And it may come out that later on there was a mistake. That can happen. That can happen. That doesn't say the Solyndra was a bad experiment. That's what happens in the venture capital world. 10 out of 9 out of 10 of those fail, even in the West. So I think these are to be understood, and both are extremely important. So Jeff, I have always worried because Donald Stokes had Pasteur's quadrant, which was a very big thing in the sense because he pointed the example of Pasteur, who went from fermentation to really how biology works, but really to really try to not conflate. Very often the big things are just based as science. Engineering is sort of just either viewed conveniently as part of science and sometimes ignored. Harvard doesn't even have an engineering school for a long time, try to get rid of it, and so on. That it's time to actually draw our diagram, which actually goes beyond Stokes in this research and development, because it's a so important part. So Jeff, why don't you say a little bit about this?
Yeah, okay, so but before I do that, let me just emphasize one additional thing, which you did say, Venky, but I kind of want to maybe, just maybe overemphasize it, which is that a lot of people equate research with science, with S dot, yes, and they equate development with T dot.
Yes.
And I think what Venky is saying is that is not an equation. That those are not equalities. There can be research of a technological nature. We call that engineering research. There can also be development of a scientific nature, where you're not actually very surprised. You're consolidating all of the science that you know in somewhat in new ways, but you're not actively seeking surprise in a scientific way. So anyway, that's just an aside there. Okay, so on this Stokes diagram, again, this figure on the left, there's a lot we could talk about. We could spend an hour on it all by itself. It's an extension, as Venky said, of Donald Stokes's Pasteur's quadrant construct. We've added 4 important new quadrants in the rear to reflect development and consolidation of knowledge. We've also made an important addition to the research and surprise quadrants in the front. So some of you may, some of you may remember that Donald Stokes had difficulty naming the lower left quadrant because curiosity-inspired engineering research seemed so inconsequential. Instead, we've given it a name, Towns Quadrant, to emphasize how consequential curiosity-inspired engineering research can in fact be. Following their curiosity to create a form with completely new capabilities, even if they didn't know what functionality the form would eventually serve, was what Towns and his colleagues did when they invented the maser and the laser. In fact, the derisive joke about the laser for many years, as many of the older folks know, was that it was a solution looking for a problem. But now, of course, we know all the many consequential problems that the laser turned out to solve.
So we probably now, we've got about another 10 minutes or so. I'll try to be quick here. The research must be, I feel very strongly on this point. Management schools are very often. I remember writing my first paper for Issues of Science and Technology, and the editor was a very good friend. He says, Venky, this is about management. I said, no, research policy requires the right leadership and the right thinking. So finally it got published, my first paper on this kind of subject with Laura Anadon and Ambud Sagar. And I think it's very important that the nurturing part is understood properly. So you nurture people with care and accountability. And when I started doing, I thought I was, I had a patting myself on the back. And then I started reading various histories of Bell Labs and so on. And then there I discovered, and the physicists and the chemists were all highlighted, like Mervyn Kelly and others. But a famous engineer who won the IEEE Medal of Honor, Ralph Bohn, was not mentioned as much, but he was actually the director of research when Bardeen, Breton, and Shockley invented the transistor. And in 1947, they brought him to the lab to show what they had done. And by the way, Bardeen was in the lab, the famous theorist working with Breton. He just didn't sit in his ivory tower. And whatever he did, Bohn gave many speeches, and he wrote a speech on research institutions and what he thought about research. That, for me, is a crown jewel, and I refer to it in my book, and in this book, Jeff and I use it even more, and I think I want to bring this, in fact, to IEEE as well in a greater way, because he, in fact, is a Medal of Honor winner. And research environments reflect human relationships and group spirit. In short, successful researchers should never forget that they're human institutions and they should place people above structure. If that message is not understood, I have failed in my presentation today. And then embrace a culture of holistic technoscientific exploration. That science and engineering are now a matched pair. It's just like you need always two people to engage, to create a family, whatever you take. And that's really important. And of course, there is the environment. The culture is very important. And of course, the whole bunch, we have a lot of stories in our book. And then you must align the organization, funding, and governance for research. If you don't do that properly, you will lose whatever research and that thinking you have. People don't just start. I wrote, when I joined Sandia Labs, and I do want to show that picture in a little while, I wrote an article, and Bell Labs, I was leaving Bell Labs, the Bell Labs News interviewed me, and I wrote an article, and I said what it meant to actually create a research organization from my perspective. And they titled it Nurturing the Novel Neocortex. And there it is always where I like to use the word, nobody works for me, I work for them. The job is to make the researchers successful, obviously there are judgment calls here. You don't throw money around. You've got to tell the weeds from the flowers. You've got to tell the flowers from the weeds and actually nurture them so that in fact that research is successful. So nurturing and providing the research and support is so important. And this should be true for all managers of any organization. It's the people who do that work, and you give them that environment, make the right, but don't isolate them. They need to collaborate effectively. So that governance part is really important. And then you fund research to achieve meta goals. Is this related to the broader issues of national security in Sandia's case, or energy, environment, etc.? And obviously there'll be proximate goals on the way, but you really want to think of the meta goal. Insulate but not isolate research from development, because it requires a different discipline. It does require more serious management in the development phase, and that's important. And in fact, sometimes it's more important. But that doesn't mean, but the research part is probably a smaller part, but it's the risk capital. Block fund people, not projects. The researcher must have flexibility, just like Horst Sommer inventing the high mobility transistor and immediately moving to the fractional quantum Hall effect. That flexibility must exist in many ways, in many parts. And the research is not simply a matter of assembling and giving them free rein. It is a matter of a delicate balance between organization focus, personal development, and individual freedom. There are a whole lot of issues here. Matrix management is very, very popular these days, etc. But who actually worries about the person? We talk about diversity and inclusion, all these features, and that person who understands the needs of the individual. And as part of that, that's why mentoring and those features are also important. So we're sort of coming to the end of our discussion here. And really, we want to summarize, embrace this culture of holistic technoscientific exploration. I don't have to go through this in detail. And then, and there are three elements in it. The scientific method is more than hypothesis testing. Embrace informed contrarians beyond peer review. Nurture people with care and accountability. That's really important. You're accountable. And I, as a Bell Labs leader, whatever, was accountable in various ways. And this is quite important. So it's not just giving a free run. And then, so the mentoring part is really important in today's world. Because in fact, very often when women and minorities don't quite make it, it's because they're not part of the social milieu the way the majority are. So how to weave them in is quite important in that and mentor. But it's true for everybody, for males, females, everybody, that they be mentored at a young age. And my department manager at Bell Labs made some important connections for me. He did it very gently, but it was very important. Hold research accountable. That does still mean ultimately there are metrics, etc., and there's performance review. So this article, the next view graph, I just show this in a sentimental way for my Bell Labs and Sandia colleagues. They forced me to take this picture when I wrote that Bell Labs news article, because every visitor who came, the young people who came whom I was trying to recruit, I would take them to the bust of Alexander Graham Bell, who would say, go off the beaten path, delve into the woods, you'll find something which you've never seen before. It was like a beacon of looking for the unknown, looking for the future, not just about scientific, but invent the next telephone, the next communications, and do the physics which is necessary for it, or the chemistry or material science. Bill Brinkman succeeded, I succeeded Bill Brinkman, and this is just a transfer, but I think that was the guiding vision for hundreds, not just me, lots of other people when they were trying to recruit and having that vision. So from 1920 to 1990s, we had, starting with the transistor to the fractional quantum Hall effect, many great things happened. And of course, there was also IBM research doing great stuff. Lots of Nobel Prizes came out of there, General Electric, etc. Again, this is just iconic. And then now what is happening is, in fact, we are recognizing we have to have constructs. Universities are not just only about the individual. It started with a whole lot of interdisciplinary centers, and we're now learning how to manage and run them in a lot better way. The risk of being somewhat immodest, Santa Barbara is particularly good at it because they were relatively new. They got a fresh start and they weren't stuck. And now lots of others are happening. That's how Stanford started with Bell Labs alumni. Santa Barbara started with a lot of not just Bell Labs, with Exxon, IBM, because all those labs were downsizing. Santa Barbara grabbed them, and it's now become a fantastic institution. And so there are new things that are happening. Computer science is done very differently. Google has DeepMind and doing it in a certain way. Tuition, philanthropy. So there are many ways this science is being executed. And I think history will judge how successful these are, but some of them are already in the right way. The future is even more complex. And in fact, our collaboration between Jeff and me started actually in 2013, before he actually came to Harvard as a visiting non-stipendiary fellow, that he and I organized a workshop along with Tolu Oromusu and a few others on really the art of really understanding the science processes, and in the larger sense, how science and technology relate to the larger society and how we can function. So Jeff, maybe you want to say a few words on it, and we'll be pretty much on time.
Okay. Yeah, that's incredible. Actually, we have a minute. Yeah. So this is, like Venky says, more of a long-term future vision. The idea is that research is really about learning, and that includes, in a recursive kind of way, learning how to better learn. And there's two pieces going forward that might be really interesting to explore and to dig more deeply into as social science gets more sophisticated. In this workshop on the left, some of you may remember it. We ran it at Sandia about 8 years ago as a baby step in that direction. As social science gets more sophisticated, let's apply it to better understand how to better nurture research. Likewise, as AI gets more sophisticated, let's apply AI to better understand how to nurture and do research. And to come full circle, this is what Venky was hinting at the beginning. Researchers shouldn't just be another special interest group trying to get more funding for research. Let's really try to make our research more effective. And that would be like a grand Bell Labs 3.0 vision for the future.
Even AI has to learn a lot, as we say in our book, about cause and effect and how it works, etc. And it's not yet ready to replace a human being. Let's be very careful on that point. But we have to start working in all of those areas. So we also have posted a set of selected readings. That doesn't mean they were the only ones. There are lots of others, and that I want to just again thank those who have patiently listened to us for a whole hour, and my friends at Sandia National Lab and elsewhere who are tuned in for having listened to this discourse between Jeff and me. So we should, I don't know whether you want to start, turn it over to question and answer, and whether you had a chance to access the chat function, which I have not done, of course, but since I was speaking.
Right. So let's continue on with the last half hour of this session, which we will continue to record, by the way. And Kathy Simonson was actually nice, and she copied, let's see, the various comments that were made in the chat during this past hour. And there's a few that I'm looking at that would be, maybe I'll sort of call out. Okay, so one question, Venky, is when you were talking about the pastures quadrant, so this slide back here, and of course many people emphasize the answer finding nature of much of the work in these quadrants. So the question is, if Pasteur himself or other famous people, Shockley, for example, if instead they had followed the Heilmeyer Catechism, how much would that have limited them? Would they actually have failed in what they were trying?
Of course, it's a thought experiment. It's not possible to answer unambiguously. It depends on the flexibility of who is running the show. So, for example, in the old days, including the DOE Office of Atomic Energy Commission, because I was funded by that way back as my graduate student, and Office of Naval Research, they had very alert program managers who then recognized that somebody had done where some directions needed to be changed. So what I need to say is that so it would depend on the flexibility of the leadership and the method, and then I think it would actually make sense. That's the really important point, not to cage the person, and you'd still make a judgment. And that doesn't mean you're always right. Bell Labs did make mistakes, and then they corrected them.
Right. And by the way, that was a question from Srinivas Nedunuri. And I echo what Venky says. It's not a one size fits all. There's many different ways to skin the cat. And the Heilmeyer Catechism can work in many situations. It's just not the only way in which things can work. Yeah. So this question just came in. Actually, I really like this one from Thomas David Nevins. So let me read it out loud. The idea of managing by covering people instead of specific projects, I think matches how creativity actually works. It might be uncomfortable for organizations since it isn't easy to quantify, but that control is an illusion in the first place. By supporting people instead of projects, you allow more creativity, and as a side effect, you get more productivity. I wonder, have you two considered how this approach matches how writers and artists work?
Yeah, so I think I've always viewed, in fact, engineering especially, because you're trying to make new things, because physics, my field, is more about understanding the natural world. Biology is understanding of the living world, but engineering is a lot about creating a new world artificially. And it's really has a lot of similarities to art. In fact, I've often viewed it, that's why engineering is more of a liberal art in many ways. And of course, society is also important. But I think the really important point here, that's you do want the creativity. I cannot tell you how creative these people were. I was just fortunate to be their leader for a few years, like not just Stormer, Gossard, Cho, Federico Capasso, etc., who kept on branching to new areas and recognized. That doesn't mean we never made any mistakes, because there's some very, but this is really important that there's flexibility there. That doesn't mean the question is, it's always an affordability. Every organization which wants to be at the leading edge, must choose to develop some small percentage, which is your risk capital, which is your risk weighted, where you will be taking chances, and there the individual becomes really important, and the leadership. Because that doesn't mean the leadership is always going to be right. I'm sure there are a whole bunch of people, just like even Vannevar Bush, who was a great person, obviously, as it evolves. So I think it is really important. It goes beyond. When I want to tell you, if you go back to that slide with Bill Brinkman, I want to show you one thing which is very important, especially it relates to Sandia National Lab. And there are people in this room, I don't know how many of them are still there, but I think which is really important. Bill Brinkman, and when I went to Sandia, there was a research advisory committee, and Bill is sort of handing over charge. I didn't have my clearance. He came back because we were giving funds out, and we were meeting, and they took a picture of Bill Brinkman and me. Brinkman, just a year ago, earlier than before he left, had created, there was no computer science organization at Sandia, a big national lab in 1986. And he created there was an engineering science lab, which is important. And he created an organization that was then called Organization 1400, focused on leading edge computer science research. And I had to build that up. And I'm very grateful that Bill had the flexible funding from the Research Advisory Committee to seed that organization. And for Bill, I asked him the other day, it was obvious it should have been done. But I told him, no, he did something very prescient, because in fact it was prescient. And today I believe that computing, and I don't know, those Sandians should talk to Rob Leland and others, because I think I was vice president when he was hired, and many good things happened in that area. So it's very important for a big national laboratory to have that, and also an engineering function, which is also reward for the future. Engineering is not only about just developing what is in science, it is about the future in a significant fashion. So it's really, and that's an excellent example how the funding has changed. Now everything comes in buckets, and that's very limiting. And it's not because the DOE managers are bad, but that's what the accountants have decided, and without realizing. It's been corrected somewhat with laboratory director research and development funds, but even they are often subject to that kind of. So it has to be viewed as a risk capital. And if the government fails on something, we don't criticize them like the Wall Street Journal sometimes does with Solindra, because we can criticize a whole lot of venture capitalists. Public funding also has to have some risk for public good. In environment, we're going to make some mistakes. In energy technologies, not some mistakes, but energy, these are public goods. So this is really important.
Yeah, maybe to amplify on that, so this is still on Thomas Nevins' question, the idea of funding people, not projects. I think one of the things that was in the background of what you were just saying, Venky, is that that's not just true at the bench research level. You know, it is true, of course, at the bench research, the researcher who's in the lab actually doing things. It's also true at the research leadership level. Research leadership also needs flexibility in order to build big new centers like what you were just talking about, Center 1400.
What I realized in writing my first book and then in writing this book with Jeff, how important that leadership was to me. I cannot say. And now when I saw Sandy, I don't want to take any credit personally or anything else. My predecessor had a certain vision. He viewed that as obvious to do, but he had the flexibility to do it. But today, it's much harder to do it, much harder. That needs to change.
Right, at all levels. It's not just the bench researchers.
At all
levels.
Doesn't
have flexibility.
And that doesn't mean Brinkman is not accountable, or I was not accountable. If I had failed, they would not have sent me as vice president of Sandia or whatever, or Harvard would not have recruited me. That doesn't mean they can't make a mistake. So it's very important that even in public funding, there should be some risk capital. And if they do that, including in technology, that is a failure. You must still spend it wisely. You want to still have successes, obviously, but nevertheless, it is important. It's the risk capital.
So another question, this one from Eli Yablanovich, who's calling in from UC Berkeley. You emphasize surprise. But is that compatible with large organizations, which generally are not all that excited about surprise?
So I think that's true. In fact, that's what has happened in many of these. Believe me, Bell Labs was a large organization. As you know, Bell Labs had some 20,000 employees, leave alone. AT&T was Ma Bell, the biggest employer in the country. But there was a vision which started with Graham Bell. I actually believe General Electric had a similar vision because of Edison. But then the people broke them up, just like people said, oh, it'd be a great thing to break AT&T up. And then, of course, they weren't. It was a different reason. It's the public service. But the other is the organization must recognize that it wants to do this public service that also might benefit them, because you can recruit and so on and so forth. One reason AT&T was chosen, Bell Labs to manage Sandia Lab. Obviously, a highly sensitive nuclear laboratory was to actually bring that kind of competence and good people into the fold. And that's why University of California, the greatest public university, was chartered to run Los Alamos and Livermore. These are important elements, but some of that has been lost because, in fact, of the value because of the short-termism. So I think Eli is partly right, but that's what we need to correct. And this includes the history of national labs. So many people have written reports on it, but never, it's very hard to move the needle. But I believe the needle needs to be moved. I see that happening in other, and if we call it research with intentionality, as we put it in ours, but it's not mean you're doing something short work. It is a long-term meta goal. So, yeah, that's why we do need to have large, because sometimes they don't have the scale. So Eli is partly correct. At least I think not partly correct. He's correct in a certain sense.
Right.
Yeah. And this is happening now in the pharmaceutical industry. They've gotten much more, but finally the government had to intervene, and they had a Manhattan-like project with the vaccines. But the research was done on the mRNAs by people like at NIH, etc. And the development was accelerated. Very important. Very important.
So here's a related question, pretty closely related question from Tina Nenoff, who's one of our senior scientists in Center 1800. She says, well, Bell Labs is defunct. Yeah. DuPont Experimental Station is defunct. GE just divided into 3 companies. How do you reconcile that there needs to be a new business model if we're going to resurrect some of the culture of these great research labs? So
I think I do have great faith in America's entrepreneurial spirit in various ways. I mean, I'm a thorough American in all my upbringing ever since college, and it is important that we rise to the occasion. When I say Bell Labs, it is just a way of describing that culture. And many experiments are happening. That was idea of 2.0, where, for example, in quantum computing, Google and others are funding research at Santa Barbara to do the early work and working in these fashions, and that's happening. Department of Energy has tried to do some energy innovation and other features. So I think those juries are out. I see some ways where, in fact, it could be, obviously some of them are going to work, but the thing which I still see missing, back to Eli Yablanovich's concept, is the scale that matrix management does have some limitations. And ultimately, you still need people who understand the person. You know, one of these things which is to be understood, why mentoring is so important. If you want to affect society, this includes national security, we want a diverse workforce, especially in gender diversity. Because in fact, not all men are the same, not all women are the same, but there are some various features, and this mentoring becomes very important. So we bring them into the workforce. By having all the other features doesn't mean we forget all the things which were done by BAST, but rather build that community which is diverse and really bring the best out of your workforce. So that it's not to be lost. The mentoring part is very important in the leadership and in the diversity issues, but that doesn't mean you forget merit. That doesn't mean you forget. They need to be brought together in union, otherwise it won't work. And so we are trying these new experiments, and philanthropic institutes are coming along in some big ways. At Harvard, the Broad Institute, where Rick Lander is now the president science advisor, he really started, biology did not do any team science the way engineering and some of the physical sciences did. And it's now changed a lot. And that's why, and including it, and NIH is changing. So those are elements which I see as hopeful. That's what we mean by Bell Labs 2.0. And it is time that national labs recognize that in a better way. I think some of the Office of Science labs are doing well, but they are chided if they do anything with technology the way it is viewed. That's why the energy innovation hubs were created, to bridge that divide during Steve Chu's time. And I believe it's important to keep trying. So the Office of Science teamed up with the Office of Technology Development, or ERE, in some good ways. And that needs to happen more and more. And NSF is doing that too. So we'll only know the answer. But I think it's important to know that China is doing this. And many parts of the rest of the world, including Europe, is having a resurgence. It's not just China. And that is the way it is evolving, because, of course, resources, either you need a large national laboratory or you have to team. And you probably need both. And private institutions can be helpful for leading edge. That's long been the case, Rockefeller University and other places, but they never will have the full scale which you need. Because AT&T had the scale, IBM had the scale, and when they broke up General Electric, it didn't have the scale. AT&T was broken up, and they separated. Another important point which economists have made for a long time: the manufacturing will be done in China and Japan or India or somewhere else. Labor will be cheap, and we'll do all the research here. It works up to a point, but eventually the R&D gets close to the manufacturing because you need to connect and so on, and you go up that value chain. It is very important that you also make things in the United States and compel that with the front-end R&D. It is not old-fashioned. It is the correct way. We learned it the hard way in the pandemic. And this is not against China or anybody else.
So Venky, along the lines of a diversity of institutions for research, yes. So a question that Celestino Corral had was, given limited funds, and other people have asked this question, I've heard it many times, does it make sense that research, at least certain research topics, but maybe research more generally, maybe we should just let the universities do it, and maybe the national labs should just do more development?
And national labs should do what?
And the national labs should do more development.
Well, I'm afraid it only works up to a point. Obviously, because the whole issues of scale. There are things which you cannot distort university. I always felt I went to university and didn't take a high-paying job in other parts because it was about the education, about bringing the generation of students. So we need to teach them the right way. That's why you want diversity. That's not just the individual. The person is important, but you need to how to collaborate and share and do all of those features because it's holistic, because nobody can be expert in one thing. But they don't have the scale. If you look at energy, and that's why even the venture model doesn't always work. In software, in some parts where you don't have big capital investments, it will work, but not where you require a lot of capital investment. That is also true for drug delivery and the drugs. If you've not learned any lesson from the COVID, then I'm afraid this country has failed. And I cannot do that. This is really important that we have national laboratories, which also, and they cannot couple to the development unless they do some of the research as well. It's just the nature of the beast, because then the research dies and the development becomes more pedestrian. I'm being a little harsh, but it's not quite right, because for a while you'll survive. I really feel the national labs have a real responsibility to bridge this divide, to really make sure that, because you have the scale, large facilities are so important. One of the things we were always proud of Sandia, it had these enormously large testing facilities, shock facilities. With shockwave physics, nobody else could do that excepting in organization 1,500 or 6,000. I forget the numbers could be all different. This is so important. It's not just development. We still needed the computer science people. We still needed the engineering science and the applied mathematics people. And we need so this is really important. The scale, the energy problems, the climate problems, the national security problems cannot be solved by a small little university.
So Venky, here's a question that I think is on a lot of people's minds. Yes. I don't know who asked it because it says unknown user, but two people liked it, Eric Langlois and Andrew Young. So the question is, as long as, oops, where did I go? Okay, yeah, the question is, as long as corporate management is dominated by Harvard MBAs with accountant mindsets, instead of scientists, engineers, and other people who think beyond the next quarterly report, short-term thinking will likely continue to dominate. I think that that's a very sensitive question. And I'm, of course, really a backer of technoscience. It's not against science. Very important to understand. It's both technology and science and linking it to society. I actually think there are many things which Harvard MBAs or Wharton MBAs or what you choose your school of your choice do good things for running of large organizations which require certain ways of running things. But even they have realized the value of what I call the inverted pyramid. That is, I work for the people, not the people working for me. And so I think many of the business schools are also changing. I've talked to Gary Pisano at the Harvard Business School. But I thought many of the things which happened,
the institutions which I know well, namely Harvard, Santa Barbara, and Stanford in some ways. When I went to Santa Barbara, the Stanford, many people wrote to me, Venky, Santa Barbara is like Stanford used to be because we got all these people from Bell Labs, from Shockley to everybody else. And Santa Barbara and Harvard has a business school, but they have their own department of engineering, technology, and management. At Santa Barbara, we created a technology management because the technologists think and the scientists think in a slightly different way. And so now I realized that what we have to do is actually create a new form of MBA as well at the master's level, where people understand the science and technology well. If it pervades so much, it's important for our public policy. And then also learn some of the other techniques. So not everything which Harvard Business School does is bad, but we have to change them and us. Both sides have to change. This is important in terms of how we educate the future workforce and develop the intellectual capacity, which includes an equal seating table of the scientists and technologists with the business people and ultimately some of the social science thinkers, etc. So you notice I have slight hope for our country because with Eric Lander becoming, I don't know him very well, but I know him reasonably, and the associate, the vice chair is Alanda Nelson, who is a social scientist and STS. So we are trying to change how this works in the science technology space. But now we have to change it also with the economic pace. For a long time, the economists and the business schools were thinking very linearly instead of realizing whole areas of politics and behavior make a huge difference. That's why AI is still very limited. It's so important that education change. So we are now developing a new program with the Harvard Business School, my successor. I had nothing to do with it. I started that to actually at the master's level, where people will understand some of the technology thinking, but also understand the other point of view. You cannot affect change otherwise. I've had many arguments. So I hope I'm making it clear as to how. So at Santa Barbara, in fact, we have the engineers running. At China, for a long period, Xi Jinping, the current dictator or chair of the Communist Party, was a graduate of Tsinghua University, which is considered the MIT of China. And a whole lot of others came out of that area. Now, whether they get now change. So I don't want to say that technologists and scientists are all knowing. They need to be an important part of the puzzle, and they got to understand the other sides. That's the holism, which is what it's about. It takes a lot of effort. And that's what I believe personally. And Jeff, I don't know whether you agree with me, but I think I convinced you on that point in our many debates.
Right, in many of our debates. And just as a side thing, there have actually been several comments along the lines of how we educate the workforce. Yes. So on both at the level of bench researchers who if they're doing research and seeking surprise, that's a different kind of mindset that they would have to learn when they're in
that's right. School. Yeah. So I think I actually worry sometimes about universities. There are things we can learn from corporations in the university, and there are things they can learn from us. And we have to blend these two. It's never going to be perfect, but it's really important in how we educate them. So I can tell you, Harvard, it was very hard to hire computer science people when I first went there. I used to get nasty notes because we were so ruggedly valuing only the individual without realizing there are other metrics which are just as important. If you really invented something new, we never counted that. And it was only publications and the individual. So there are whole areas of performance review in universities, including and I wrote some of it in the Rees to panel, and I take heart, many of them are changing. Harvard has changed. That doesn't mean we are perfect. And Santa Barbara has changed, Berkeley has changed, and this will evolve. And we need to do that, but we need to break these silos and boundaries. This includes the humans, the social scientists, the artists, so that we, in some appropriate way, in that balance. We still need the specialists. We still need some really hardcore engineers and scientists. That's okay. It's not for all, but you build the ecosystem in the right way.
Right. So this also gets to the question of measurement. As we know, OMB is a very powerful institution, which exerts a lot of influence over the United States, including DOE and Sandia. And the idea that what you measure typically is at the beginning of, and it reflects itself in our own performance review. You at the beginning of a year, you write down what you hope to accomplish. And at the end of the year, you're judged. Did you accomplish that or not? On time, on budget, all that kind of stuff. But research is so different; it's very tricky to measure.
Yeah, it is, of course. I think we only know it whatever retrospectively,
Right.
But I think the emphasis at Bell Labs always was what is the new that you're trying to do? At least imagine that. And if it turned out in the process of the year, it changed. Nobody was monitoring me every day of the week, right? And then and over some period, your publications, how others are, there are ways where you can actually do that. And sometimes people had a long leash. As Federico Capasa told me, Alcho took 10 years to do MBE, and MBE is such an important technology. And that means John Galt, who came as vice president of Sandia a long time ago, let him run his leash. I benefited from that. And then others benefit from what I encouraged. So this is really, that culture really becomes important. So John Galt knew, or Bill Brinkman knew, that we need to hire some of these other people. That doesn't mean they won't make mistakes. I'm sure John Galt, I made mistakes. So I think this is really important that the performance review be judged more holistically where there is a time involved. You always start with some project. You start some project and you immediately change it. That's what the nature of research is. It's about surprise, doing something different.
Yeah,
it's a cultural thing. So that doesn't, but if you keep doing this and never succeed, then you may say there is a time. That doesn't mean it is not infinite. It's usually some long period of a few years.
So we only have a few minutes left, but there's one last question.
And so you spent a lot of effort in recruiting. So all the technical leaders were active in recruiting in a very serious way. So we took the recruiting very seriously. It was not just a hired hand. We were looking for the broader potential. That doesn't mean you were right every time. In Harvard, it was the opposite, where only you had to be a Nobel laureate almost. But now, in fact, we hire and roughly 50% get their tenure, which is a decent number. That means you're really batting reasonably well. You're being selective. All the faculty show up. We debate this and so on. So there's a balance. There is a balance. There's not a free lunch. So I think our time is sort of up.
Well, one more question. This is actually my favorite question of all the questions so far. It's by Asmaret Noggle, who is one of our younger staff at Sandia. She asks, so to paraphrase, we've sort of focused almost a little bit more on system level changes, large scale changes that research leaders, at the VP level or director of labs, level can make. Are there things that individual scientists and engineers can do differently in order to improve the environment, the integration that you're talking about?
Of course, we have some of it in our book, but it's much more. It's a very important question. That's what I mean. We have to develop and mentor the young person. So we keep meeting with them regularly, not to micromanage them, but to look at avenues where they can branch out, to have the collaboration. It's like when I wanted to, and allow them to interact. There are professors who want to control their students completely. But I, in my lab, allowed them to work with Herb Kromer, and I have papers with them, and they learned, they had other people. So the same thing has to happen. Don't stovepipe them. Allows them, mentor them, encourage them. And that's so important. That's what is so important to get the diversity in the workforce. We do need more women and minorities for very good reasons, not for some issue of fairness or anything else, for the success. So, and the mentoring becomes, and the environment where people are learned that this is important. So at Bell Labs, we were competitive, but we're also one large family. Sandia is a family, and that family part has to be understood, and the leaders have to encourage that. That's what I mean. People don't work for me, I work for them. And that's so important. If I missed that, my apologies, but I'm trying to appeal to a very wide audience, and I'm happy to spend time on those mentoring aspects. There are some very important aspects of that.
Yeah. And I guess I would add to that in response to Asma's question, is that the mentoring, maybe it can go both ways. It's not always leaders that are mentoring staff or whatever. Actually, many times staff know better than leaders.
Of course,
and they need
that's
to
why being part of the peer community, who you eat lunch and dinner with, and varied people. Yes, absolutely. So that environment has to encourage that.
So it's 11 o'clock.
I want
to thank everybody the audience. You've been terrific, and all these questions. I wish we could answer more of the questions or discuss more of the questions. And of course, thank you so much, Venky, for being part of this.
Well, thank you. I'll stay on for 2 minutes or so to chat with you, Jeff.
Yeah, okay, but we'll call an end to the session. Thanks, everybody.